Hello and welcome everybody to our talk for this year's regional conference in permafrost. And I would like to give you my talk about a recent study that might be published already, but at the moment, as of today, is accepted. It's on evaluating a deep learning approach for mapping retrogressive thaw slumps across the Arctic. I'm I.Nitze from the Alfred Wegener Institute. And in this study, I would like to thank my colleagues Konrad Heidler, Sophia Barth, Alex Tagowitzka, and Guido Große for supporting me, especially Konrad, who did a lot of the coding work. Although we are at a permafrost conference, and I'm pretty sure that you know what retrogressive thaw slumps is, I would still like to give you a short introduction to them. So they're typically erosion features, which we find especially in very ice-rich permafrost, especially in formerly glaciated terrain. And it's a typical mass wasting process, which has strong implications on local to regional aquatic ecology, on hydrology, on biogeochemical cycles, and also the carbon cycle on its own. We see some example here on the top left from the Bykovsky Peninsula, which is a nice coastal thaw slump. And the second example on the top is the Selawik slump, which my Alaska colleagues pretty much notice instantly. They can be pretty dynamic and quite small. So they range from very small, just a few square meters, to up to about 1 square kilometers, which are kind of the mega slumps, which we find in Batagai or some other places in northwestern Canada. The problem is they often remain undetected. So due to their scattered distribution and their small size in very remote areas, it's pretty hard to track them. So they're typically clustered. So we see big clusters in northwestern Canada at the ice marginal areas of the Laurentide ice sheet. So the Peel Plateau is, for example, quite prominent. Banks Island, Victoria Island. In Alaska, not so much. The Selawik Slump, Noatak region, the Brooks Range foothills. But there are also many unknown places in Russia and Siberia where we do have thaw slumps, but they're not thoroughly mapped. And they can be pretty dynamic, as we see here on the bottom. So these are rapid eye images where I delineated thaw slumps in 2016. This is on the Taimyr Peninsula, which is also one hotspot, which is not very well known. And here we already see like how they expand over time. Due to their importance on local to regional scales and even bigger scales, if we count them all together, it's quite important to study them, how they're distributed, how they change over time, if they change with the changing climate, and how their interactions are with the landscapes. So far, most studies are mostly local scale with high resolution data. They're pretty accurate, so it's mostly based on digitization and quite simple methods. But that requires high manual effort and is kind of limited to really small local areas. So we don't really know the big picture. On the other hand, there are studies that focus on regional to continental scales, but they typically have a lower accuracy due to the low spatial resolution. So our target is to have a segmentation of retrogressive thaw slumps, so to get their footprints, to get polygons, for example, or raster masks for them, and the combination of the good features. So we want to have accurate results with little manual effort, but on large spatial scales. Over the past years, there's been a lot of progress in image analysis and object detection, object segmentation, mostly in everyday imagery for detecting certain objects from photography, like you see here on the left. So this is a nice photo from me in the field. There are algorithms based on deep learning or artificial intelligence, which are looking for the entire image and the content of the entire image, and not only on pixels, which we have done in the past for remote sensing imagery. So here on this one, you can nicely see there is a detection of a person, of a backpack, and other features. And over the past years, this has been also implemented in remote sensing work, and especially also in permafrost. Although in permafrost, we're a bit slow with adapting these new technologies, but there are certainly some studies who are kind of trying to leverage these capabilities of these deep learning methods. For example, Zhang et al. And the group around Chani Witharana, who are working on mapping ice wedge polygons on very high resolution data with deep learning methods. Also Ling Cao Huang and colleagues who are mapping retrogressive thaw slumps on the Tibetan Plateau. Based on the successful application of these image analysis workflows and image analysis algorithms, we set up a data processing pipeline which uses remote sensing input data, create a deep learning model, which outputs retrogressive thaw slump footprints to have that automated and to analyze the data in the background. So we created a highly automated workflow which takes care of the data management, of data processing, augmentation, which means adapting the training imagery to increase the training size, but also to introduce some noise, some rotation to better generalize the model and to have a more transferable and generalizable model. The workflow also contains automated model training and validation, inference, which means then the final application of the model. So we put data into the model and receive footprints from also unknown areas to really apply the model over large regions. And all that is implemented in Python based on PyTorch and many packages which are working that. And the code is on GitHub. So you will have a link to that later on so that you can also use the code, improve it, and create your own models, improve models, and run the entire processing. To test our model and the application, we chose 6 regions across northwestern Canada and Russia, which are Kolguyev Island in Lena River slumps in Russia, and Herschel Island, Taktoyakto Peninsula, the Horton Delta region, and Banks Island in northwestern Canada. We applied a regional cross-validation where we trained the model on 5 regions and validated on a 6th one and rotated that through all regions and all potential setups. As thaw slumps can look very differently depending on the sediment they are sitting in, on vegetation which is around, if they're on a coastal setting, more at valleys or on lakes. We try to incorporate all these different attributes that they can have. Now let's come to the data that we used. We used mainly planet surface reflectance scenes from 2018 and 2019. They have a spatial resolution of 3 meters. They contain 4 bands, which you see here on panel A. So they are multispectral in blue, green, red, and near. Here on the bottom you see an example of a thaw slump in the Horton region, which is pretty big in a color infrared image. On top of the multispectral data, so the 4 multispectral bands, we also calculated the normalized difference vegetation index, as thaw slumps are pretty much characterized by bare soil surrounded by vegetation in many areas. We also used Landsat trend images from previous publications of me with Tesla cap brightness, Tesla cap greenness, and Tesla cap wetness trends over time. So that also contains a multi-temporal approach, which gives us information on the changes that happened over the past years in that area. So here we nicely see in blue actively eroding thaw slump areas. On top of that, we also used the Arctic dam which is available for most regions across the Arctic. There are some gaps and holes here and there which might cause some trouble, but overall they're covering most of the areas quite well. There we used relative elevation, so detrended elevation. On top of that, we calculate the slope in degrees, and we used Google Earth Engine for calculating all these values. In contrast to most standard deep learning algorithms, for example, Mask RCNN, which only takes 1 or 3 input bands, we're here able to use more bands. So we have a higher density of information and more variable information. So we can use a custom number of bands, in our case 9. And of course, this is a supervised classification method. So we need some kind of ground truth. So we created training data as polygons and delineated thaw slumps manually. For this study, we went through 2 iterations. So one person, one trained person, digitized them at the first time, and then they went through a second person, which was mostly me, providing feedback and changing the polygons if necessary to have kind of a standardized way to have good ground truth. But still, it is sometimes tricky to really have a high quality input data. As output data, we have raster values. So we have the binary raster, so which means 1 for retrogressive thaw slump and 0 for background values, but also the probability values. And on top of the binary raster values, we also provide vectors. So just a shapefile, polygon shapefiles with the outline or the footprint of the retrogressive thaw slump. The output data have a resolution of 3 meters. And here in this table, you see the statistics. So we used over 200 images, way more than 1,000 digitized thaw slumps, more than 200 images used. And the images are later even split into a lot of small tiles. On the next slide, you get some bit more technical insight into the model and how we used it. So we're trying to focus on the regional transferability, as we see this is paramount for mapping thaw slumps across large regions in the Arctic. So therefore, we chose these 6 regions. We proceeded with a 6-fold cross-validation on a spatial basis. So we used 5 regions for training, 1 for validation, and rotated through all regions. Our workflow is so flexible that we can use different architectures, backbones, loss functions, etc. So it's easily configurable. So here for testing, we chose 3 quite successful architectures, which are UNet, UNet++, and DBLAP v3. There are a lot more, but this is more kind of for evaluation. We use different encoders based on ResNet, so ResNet 34, 50, 101. And in total, we performed 54 experiments. So we iterated through all combinations. And for the best 3 regions, we also run a full training. So for running these experiments, we used a condensed data set. So we only used tiles which also contain thaw slumps. And for the full training of the best models and the best 3 regions, we added another 20 epochs. For evaluating our models, we used accuracy for the overall accuracy. So this is a binary classification / segmentation. And for class-specific accuracies, we used intersection over union, IOU, F1 score, and precision and recall to see the balance of the classification. Now let's switch to 2 detailed examples that we processed. The upper one is in the Horton Delta region, right by the coast, just south of the Horton Delta in northwestern Canada. And on the bottom, we see an example from the Lena River slumps, which are on the eastern banks of the Lena River, about midway between Yakutsk and the Lena Delta. So here in the CV model example, we see the probabilities that this is a thaw slump by the cross-validated model. So these results here are completely independent and trained in the other regions, and here the inference in that region. So for the model, this area is unknown, respectively. The black outlines are the ground truth. So this is kind of the outline or the footprint of the thaw slump, and the more intense the color is red, the higher the confidence of the model that this is the thaw slump. So we see here in the upper model, in the Horton region, that there are some parts that are better classified and where the model says, okay, I'm pretty certain that this is the thaw slump. These are typically close to the head wall. So here we already see that this area might be favored and that the model is more certain. The same in the Lena example. So the bottom one is pretty simple. It classifies very well. And the bottom, the smaller, more longer slump, it's not perfectly modeled, but still quite good. And for example, we also have the full model. So when that region is already known to the model, so this is now a model that covers the entire all 6 regions and is trained on all 6 regions. And there, if we have that trained in a certain region, then the model is pretty confident for most areas and for most locations. Our initial aim was to create transferable models so that we train in a certain subset and expand that analysis to a large region and still get a good performance. So in this figure here, you see the classification performance for the different regions. On the left-hand side, you see the one sorted by epochs, so the gradual improvement or gradual change of the model. And on the right-hand side, you see that sorted by the metrics, so from best to worst models. Here we have all the models in there per region, be it architecture or encoders. So we have a lot of statistics that go in here. Different colors, you see the regional sets. So the best 3 models, for example, are Horton, Lena, and Kolguyev. So in that region, the models perform quite well. In Herschel, they don't perform that well. And in Banks Island and Tuktoyaktuk, they are pretty bad. So we see large differences between the different models. And we see also that by the ranked one, where it's a bit easier to pick up the differences. We applied the same analysis, not for regions, but also for architectures, where UNet++ came out as the overall best architecture for mapping thaw slumps across different regions. The other 2 architectures that we tested, UNet and DeepLab v3, performed quite similar. Okay, let's sum up this talk a little bit. So in this little project, we create an automated configurable deep learning workflow to map retrogressive thaw slumps. We used planet input data with 3 meters spatial resolution and other free data sources. And we were able to produce good results with kind of a variable transferability. So in some regions it worked well, in some it didn't. For upscaling our analysis to the Pan-Arctic, which is kind of the ultimate goal, we need more training data and especially more standardized training data. So it showed that even the creation of these training data by digitization can be quite a tricky task. So there are no really standard protocols that we could follow. There could be user bias. How do we delineate a thaw slump? What is a thaw slump in general? So these are kind of important questions that need to be solved. Therefore, I would like to invite you for feedback and to kind of work on that together. Upscaling, of course, is the next step to do that for highly affected regions across the entire Arctic. And in the end, we would like to have a continuous monitoring and also model improvement. So the good thing is with deep learning models, we can retrain them add new data, and then improve the models gradually. Even after the summary, we have a little bonus. So the methodology and the workflow is so much automated that we can also add other data. It doesn't have to be thaw slumps. So we can add any other features where we already have data sets, for example, pingos, which you see here on the left-hand side, where you see the pingo probabilities overlain on the Arctic Dam and the Northern Seward Peninsula, or to create water masks, which here trained on the Pearl water data set. And for future plans, we also working on adding multi-class capabilities that we can lump them all together in one model and have more flexible input data. At the moment, it's more or less hard-coded for the defined 9 input layers and planet data. But yeah, adding, for example, Sentinel-2 data will add even more value to the workflow, as then we can really rely on completely free data, which planet data are not. And with that, I would like to thank you for your attendance. And I would really like to hear back from you. Really feel free to share training data. I think that's the biggest lag that we have right now. Here we have a pretty automated workflow where we can incorporate these training data easily. You can contact me, the best via email or here on the conference. You find the code of this study on my GitHub repository and also the data. So there's a shapefile with vector data, which we used for training, and also some additional scripts for handling data. I thank you for your attendance and hope to meet you at the conference.